Right, hello. So this is going to be the first of a handful of, video solutions I'm going to post for test one. So on the recent recitation worksheet, I included a few review problems for the test. Like it says there, this is in no way meant to be a comprehensive review for the test. I just looked over, if you look in the week 5 module, there's sort of like a general idea of what to expect on the test, and it had a bunch of different problems, and I just pulled some of those problems and figured I would talk about them, because I figure it this way I can talk a little bit about maybe my approach to when I see a differential equation, what might I do, and my sort of general method for solving all of these. So here I'll have problems 1 and 2, and then I will have the rest of the problems in different videos. So problem 1 on this worksheet is just a standard acceleration, velocity, position problem. And so I've got almost everything you need to know for these problems up here on the board. These are mostly just straightforward integration. So as long as you can remember this progression, that if I start with acceleration and integrate, I get velocity. Next, if I integrate velocity, I get position. You should generally be fine. This problem just gives us a formula for the acceleration along with 2 initial values and asks us, okay, let's find the position. So we'll have to integrate a couple times, deal with some initial values. But otherwise, this is mostly just going to be integration. There are other problems occasionally where you will see like word problems associated with this, and so definitely look, I think 1 or 2 worksheets back. I think 2 worksheets back maybe. So the week 2 or the week 3 worksheet maybe. There was a word problem that involves this kind of stuff, which was maybe a little more involved. So I highly recommend going back to look at that, and the solution to that is also posted on Canvas. So here we're given this acceleration, and we want to work our way up to position. So all we're going to do, we're going to integrate this function, and so here I'm actually just going to go right ahead and replace this square root in the denominator with a -1/2 exponent dt. This is just because it makes it easier to integrate. I can keep track of those exponents. So here, I just add 1 to get 1/2 and then multiply by the reciprocal of that. So this should give me 2t plus 4 to the 1/2 plus v naught. And this is the velocity. And so now notice here, I know what the initial velocity is. I know that the initial velocity is -1, so I can just immediately substitute for that. And so now to find x of t, there's actually only one more step here. We know that x of t is equal to the integral of v of t, which is just the integral of 2 times t plus 4 to the 1/2 minus 1 dt. And so I can just integrate this term by term, add 1 to the 1/2 to get 3/2, and then multiply it by that reciprocal. So I should get 4/3 t plus 4 to the 3/2 minus t plus x naught. But here we know x naught is equal to 1. And so that actually just wraps up this problem. So like I said, I think the biggest thing to really just take note of here is remembering this progression. So just acceleration, integrate, velocity, integrate, position. And again, look back at that previous worksheet if you want a slightly more challenging problem kind of using this stuff. All right. So now I'm going to do problem number 2 from this worksheet. And so this asks us to solve the differential equation. Subject to the initial condition, y of pi over 2 is equal to pi over 2. And the differential equation we're given is dy dx is equal to cotangent x dx. Or sorry, not dx, just cotangent x. Getting a little bit of ahead. Not that. Dy dx is equal to y times cotangent x. Sorry. It's getting a little bit ahead of myself. So we want to solve this. So generally, if I'm given a differential equation and I don't know exactly what to do, because so far we've learned sort of a handful of techniques we can throw out these differential equations. First thing I want to look to do is separate it. So I'll just try to split up the variables. If I can do that, great, I can integrate it and I can move on. And so in this case, if I was going to do that, I would want to look to move all the y's to one side, all the x's to the other side. And so if you notice, in this case, I actually can do that. Because I can just flip this y over to the left, and I can swap the dx over to the right there, and I've separated the variables. So here, this is just separable. My general progression when solving these, if I'm given one that I look at and I don't immediately know what technique I'm supposed to use, I always like to check, is it separable first? Spend a few minutes, can I separate out the variables? If I can't, then I kind of go through the progression and check for some of the other forms that we know how to work with. And so a lot of the other techniques we have begin with sort of a set form for how you can go through that technique. And so I would then kind of start to look to maybe divide by a few things or multiply by something to sort of look for a known form. But since this is separable, we can just integrate both sides. So we get that the integral of 1 over y dy is equal to the integral of cotangent x dx. And now I'm going to, I need new markers. I'm going to pull this integral out. We know how to do 1 over y. Cotangent x will take us a few more steps. So this is equal to cosine x over sine x dx. And so this actually we're just going to solve with a u substitution. So you should be able to do this both for tangent and cotangent, where you just let u be the denominator of this function. And then we nicely get that u is maybe up to a negative sign. In some cases, u is just equal to what's remaining. And so if you notice, this is actually just equal to the integral of 1 over u du, which we know is the natural log u plus c. And since we also know the integral of 1 over y, well, and of course, so then we should go back and substitute here for sine. Since we also know the integral of 1 over y, we know that the natural log of y is equal to the natural log of, and so this is a thing we've seen a few times before. So remember, if we have an expression that looks like this variable here can sort of secretly be written as the natural log of some constant. And so the reason we can bring this in and just multiply is because basically whatever this constant is, it can be written as the natural log of something. And so as long as this is the natural log of something, well, then I could technically bring that something in and multiply, but since we don't want to just keep renaming constants, we just rewrite it like this. So if you have an expression like this, you can kind of make your life a little easier and bring the c in. And then we can just raise both sides to the e and get that y is equal to c times sine of x as an almost done solution. But we're not quite done yet because we need to solve our initial condition. And so remember, our initial condition tells us that pi over 2 is equal to pi over 2, or sorry, getting ahead of myself again, is equal to c times sine x sine of pi over 2. So that's our initial condition. Sine of pi over 2 is equal to 1, and so this implies that c is also equal to pi over 2. And so actually, the solution we would want would be pi over 2 sine x. So yeah, that would be the solution to that. So like I said, separable, separate, integrate. Don't forget the initial condition. I know that would definitely be a mistake I would make on a test where I'd do all of the integration, be so happy that I got done with the integration, circle my answer, and then forget about c and move on. But so remember those last steps. So like I said, next few videos I'll just kind of keep working through some problems.